The power grid is pretty much the lifeblood of our modern world. It's this vast, ridiculously complex machine we rely on for, well, everything. But here's the thing. It's also pretty vulnerable. When something goes wrong, what engineers call a fault, maybe a tree branch falling on a line or just equipment failure, it can set off a dangerous chain reaction. So, how in the world do engineers keep this whole thing from collapsing? Well, the answer, and this might surprise you, lies in a brilliant piece of math from over 100 years ago.
So, here's what we're going to do. First up, we'll dive into what actually happens when the grid faults. Then we're going to look at the huge difference between a nice, orderly short circuit and the much, much messier reality. And finally, we'll uncover the genius mathematical tool that lets engineers bring order to that chaos and ultimately build a safer grid for all of us.
Okay, so let's start with the main problem here. Now, engineers have a name for this, a fault. And really, it's just any kind of weird, abnormal flow of electricity. You can think of it as this constant threat that's just lurking inside the wires that power our entire lives.
I mean, just think about it. Our grid is this incredible marvel of engineering, right? It's a sprawling network of power plants, massive transmission lines, all the way down to the wires coming into your house. But that very complexity is what makes it so open to these faults, which can pop up anywhere at any time.
Okay, so this is where it gets really interesting. You'd probably guess that the most catastrophic failures are the ones that happen all the time, right? Well, it's actually the complete opposite. You can see right here, a staggering 70% of all problems are just a single power line shorting out to the ground. The most severe type, a big three-phase fault, is thankfully the rarest, happening only about 5% of the time. And believe me, that distinction is absolutely key.
So since we know these things are going to happen, there's no way around it, engineers have to be constantly studying them. This whole process is called fault analysis, and it is so crucial. It gives them the exact data they need to pick the right protective gear and make sure the entire system stays stable, even when something goes wrong.
All right, so to really get our heads around the solution, we have to start with the weirdest case, that tiny 5%. It's called a symmetrical fault, and even though it's the most destructive, it's also, believe it or not, the easiest one to figure out.
So what makes this fault so orderly? Well, it's because all three of those big power lines, the three phases, get hit all at once, and in the exact same way. This unleashes a massive surge of current, but it's perfectly balanced across all three lines. And that balance makes the math, relatively straightforward.
And this chart, wow, this shows you exactly what happens in those first few fractions of a second. I mean, just look at that spike. The current just explodes this incredible peak almost instantly. Then it starts to die down and finally settles into this new steady but still really dangerously high level.
So engineers have broken this whole event down into three distinct stages. The best way to think about it is like a lightning strike. That sub-transient stage, that's the initial blinding flash, the moment with the most energy. Then you have the transient stage, which is like the rolling thunder that follows as all that energy starts to fade. And finally, you get the steady state, which is like that low hum you feel in the air afterwards. Understanding every part of that storm is critical if you want to build equipment that can actually survive it.
Okay, but that was the easy part, the orderly part. Now we've got to face the messy reality, the other 95% of faults that are, well, total chaos. And this, right here, is the heart of the problem. Unlike that neat and tidy symmetrical fault, these unbalanced faults only mess with one or two of the power lines, and that throws the whole system completely out of whack. The currents aren't balanced anymore, they're all over the place, totally unpredictable. And trying to analyze them with the usual math? Forget about it. It's almost impossible.
You have to imagine being an engineer back in the day. This was a huge roadblock. I mean, how are you supposed to build a safe power grid when 95% of the things that can go wrong create this electrical chaos you can't even predict? It seems impossible.
But then, right when it seemed like an unsolvable problem, a solution appeared. And it came from an engineer named Charles Fortescue, way back in 1918. And this guy, he came up with a mathematical tool that was so brilliant, so elegant, that we still use it as the foundation for all this stuff today.
And the name of this genius hack? Symmetrical components. And what it is really is a kind of mathematical magic trick. It lets an engineer take any chaotic, unbalanced mess of currents and voltages and magically break it down into three separate, perfectly balanced, and most importantly, easily solvable sets.
Think about that for a second. The idea itself is so simple, but it's absolutely revolutionary. You're not trying to wrestle this giant, chaotic monster anymore. Instead, you solve three much simpler problems. You're breaking the chaos into manageable parts, and suddenly, the impossible becomes possible.
Okay, so what are these three pieces? First up, you've got the positive sequence. Think of this as the grid in perfect health. Everything running smoothly, just like it's supposed to. Then there's the negative sequence. This is like an engine running in reverse. It actually creates these braking forces that can make giant generators overheat. And finally, the zero sequence. This is a special kind of current that can only exist if there's a connection to the ground. And that's huge because it's the secret key to understanding that massive 70% of faults we talked about, the ones that go to the ground.
And this diagram, this is where you can really see the magic. At the bottom there, you have the total mess, the chaotic, unbalanced signals from the actual fault. What Fortescue's method does is it acts like a prism, but for electricity. It takes that messy, jumbled signal on one side and splits it out perfectly into those three pure, clean, and totally understandable component systems you see at the top. It literally turns one impossible problem into three simple ones.
Okay, so you might be thinking, that's cool math, but so what? Well, this is way more than just some elegant equation on a chalkboard. This mathematical tool is the actual foundation that allows engineers to build a grid that can protect itself.
So, let's get down to it. Why does all this complicated math actually matter in the real world? Why do we spend all this time analyzing something that might only happen for a split second?
Because every single number that comes out of this analysis has a direct physical impact on the real world. The results tell engineers exactly how big and strong a circuit breaker needs to be. It's what lets them program those super smart devices called protective relays to act like tiny lightning-fast surgeons. The second a fault happens, they can identify it and surgically cut out only the broken piece of the grid, leaving everything else running. This is how you stop a small problem from turning into a catastrophic equipment failure or even a citywide blackout. You know, Fortescue's idea from 1918 was an absolutely brilliant solution for the power grid of the 20th century. But today, our grid is getting so much more complex, right? We've got renewable energy coming from all over, smart technologies everywhere. It just makes you wonder, right? It leaves us with this really critical question for today's engineers. What new mathematical tools, what new genius hacks are they going to have to invent to keep our lights on for the next 100 years?